person here. And only a handful of y'all online already. And so everybody who's here gets extra credit just for coming to class on time. So, and Sunny's the only one who showed up in person. Hello, Sunny. All right, so, yes, so keep coming to class on person and y'all will be good. All right, so today we are going to be talking about estimation. What do you have on Wednesday? Test.
An exam.
Yes. Exam, indeed, an exam. So we will have some time at the end today for specific questions. We won't have a bunch of time, so it won't be like a full review session like we did last time, but there will be opportunity for questions therein. But any questions about the exam right now, not necessarily about material or questions you have about how to perform tests or anything like that, but any general questions about the exam? Will this chapter be on the test? Yes.
Will there be a lot of vocab?
No. In fact, I'm not sure if there will be any specific vocab. I mean, you'll have to know things like reject the null, retain the null, things like that. Yes, so you will get a cheat sheet just like last time. That cheat sheet has to be, what did we do last time? Just one-sided? So let's go ahead and make, what's that? Oh, okay.
It was one-sided.
So let's go ahead and make it one-sided again. And the reason I'm doing it one-sided is because for the final exam and the third exam, you'll get two-sided, and I'm trying to help y'all budget your space a little bit here, because as we start getting into more complex things, there are going to be more equations to write down and whatnot. So again, just one-sided. Make sure you've got a calculator that works. Again, your phone can't be used as a calculator. Yeah. Other questions? Cool. All right. So again, today we're talking about estimation, but what did we learn last time?
Repeated measures testing.
We did learn repeated measures testing. And when would you use a repeated measures test?
When it's
Yes.
pulled from the same sample?
Yeah, exactly. So you and Sunny were saying the same thing. So it's the same group, right? And so if everybody in this class were my participants, and we were doing the driving test we've talked about, everybody in class would drive normally, and then everybody in class would drive while trying to text, right? So that's repeated measures design. What's the benefit of trying to do a repeated measures test? Why would we want to do that in lieu of a between subjects test?
You don't have to find as many participants.
Yes, exactly. Yeah, so not as many participants are required to run that test. And why is that?
Because they're pulled from the same group.
Because
yes. Yes. Yeah, so everybody serves as their own control, right? You're reducing any of the error associated with sampling in general. And so by having everybody serve as their own control and calculating a different score for every participant, that different score is then what you're actually going to be using to get the sum of squares, the mean, variance, etc. You are reducing one of the major sources of error, right? And so again, when we are doing our repeated measures test, we're going to have two different measurements. One could be a pre, one could be a post. They could be two different types of treatment, etc. Right? And so for every participant, we're going to have a set of scores for time 1, and then we're going to have a set of scores for time 2, and then we're calculating our difference score, right? And so it's going to be 2 minus 1, or time 2 minus time 1, rather. So you get 1, -4, 3, right? And so now, with the repeated measures test, everything we do is based off of these difference scores. All right, questions about what we learned last time? Cool. All right. Here's your fun fact of the day. An art collector once paid $10,000 for a, quote, non-visible sculpture created by actor James Franco. The artwork was billed as an endless tank of oxygen. So yes, an art collector paid $10,000 for literally nothing. If that doesn't tell you how pretentious modern art can be at times, I feel like, although part of me thinks this has to have been some sort of joke or just fundraiser, but alas, somebody did pay that. And because we're getting close to Halloween, I get to start giving my favorite puns associated with stats, including this one of what idiot called it a randomized clinical trial controlled with placebo and not a trick or treatment. Also, you call that a normal distribution. What do you call that? A paranormal distribution. All right. Okay, so today we're talking about estimation. And estimation is something you're going to see a whole bunch now leading up to the election, right? Because every poll you see is going to have what they call a margin of error, right? And that margin of error is me saying, okay, I think that Joe Biden's number is here. I think that Trump's number is here. I think that Joe Jorgensen's number is here. But we have some uncertainty, right? And so you may hear things like 2 candidates are in a statistical tie, right? They may be 2 points apart, but that margin of error is 3 percentage points, which says that that error could just be due to chance, right? And so what we're talking about today is essentially that margin of error. So in general terms, estimation uses a sample statistic as the basis for estimating the value of the corresponding population parameter. Although estimation and hypothesis testing are similar in many respects, we actually use them complementary, right? And so we'll typically throw an estimation on, as you'll see at the end of the lecture today, I'm going to show a little video about why p-values are not necessarily the greatest things to use. And so having an estimation value tends to be a better representation of the true population difference, the true population mean, etc. So this complementary nature is demonstrated when estimation is used after a hypothesis test that resulted in rejecting the null hypothesis, right? And so if we say that there is a difference between your driving performance when you're driving normally and when you're driving while texting, we may reject the null hypothesis and say that, yes, you are a worse driver on average than, or when you're texting rather, than you are normally. But how big of an effect is that, right? We've talked about effect sizes. And so this is going to be kind of another approach to that of estimating what is the overall magnitude of this effect. It's slightly different in that it's not standardized across tests, but it is an estimation, an approximation of where that true value lies. So if I said All right, can you hear me now? All right. Thank you for the inundation there. All right. I don't know why the Wi-Fi every so often kicks out. I apologize. Let's try this again. Thank you. It's good to be back, Caleb. All right, one more thing and then we'll get going. All right. So Zoomies, what was the last thing you heard me say? I mean, before I went away. Null hypothesis. Okay. Yes. So you're using this estimation wherein you have a, sorry, let me get over here, wherein you have a value and you're trying to project a certain degree of certainty, right? And so let's say I was going to try to predict what my individual score was going to be on exam 2. And I said, I've got an algorithm that suggests my score is going to be 90% plus or minus 5%. And we'll talk about confidence intervals in just a minute, but we'll say this is the 95% confidence interval. And so I can say with 95% certainty that my score will be somewhere between 85% and 95%, right? And so it allows me some degree of uncertainty, right? Think about now during hurricane season, when you look at those cones, right? The projected cones, the width of those cones is that estimation, right? It's not how big the hurricane is going to be. It's where do they think the eye of that hurricane is going to be. And you can see that the further out they get from where the hurricane is currently, that bigger that estimation has to be, right? And so it's an approximation as to, in that case, position, or in this case, numerical value, etc. It's also common to use estimation in situations where a researcher simply wants to learn about an unknown population, right? And so this is the entire foundation for political polling, right? You're not going to poll all 300 million potential voters in the US, probably less than that, but potential voters in the US. You're going to poll 1,000 people and say, okay, we're going to try to infer from this 1,000 people what the other several hundred million people believe and feel, right? And because it's just a sample, we have to project some degree of uncertainty. And you get this just kind of intuitively, right? If you look at a whole bunch of polls, they're going to bounce around a whole bunch, right? Even from poll to poll at the same time. And it's because you have that sampling error. And so what we're trying to say is that with an estimation probability, the likely value of somebody's poll numbers is probably between plus or minus this level, all right? And so we're selecting a sample from a population, we're getting information about that sample, and now we are presenting some degree of uncertainty. And so keep in mind that even though estimation and hypothesis testing are inferential procedures, they differ in the type of question that they're answering. A hypothesis test, as we've done, is addressing the somewhat academic question concerning the existence of an effect. All right, that's why we have that binary. Reject the null hypothesis, retain the null hypothesis. We're trying to understand the foundation in the world, but whether there's an actual effect or not. Estimation, on the other hand, is kind of much more of an applied answer. How much of an effect is there? What is the amount of time that your reaction time is slowed when you're texting and driving? Right? From a basic research perspective, right, a purely academic question, we want to know, is the mechanism by which texting affecting driving potentially your attention, right? And if so, we would have very theoretical concepts that we'd be testing directly for that. But maybe from an applied perspective, as a lawmaker, you want to say, okay, well, how much of an effect does texting have on driving? So again, we are basing a lot of what we're doing with these estimations off of a sample from an unknown population, right? In this case, it would be after the treatment. So let's say we know beforehand what a population's risk of getting COVID is, but we don't know afterhand, after they get the vaccine, what their risk of getting COVID is. And so we're going to take a sample from everybody that's gotten a vaccine and then try to estimate the mean. And from there, we'll have that estimation, that degree of uncertainty. So this just, again, serves to highlight the difference between the two. I'm not going to read over all of this, but just to give you the high level, the goal for the hypothesis test, as you know, is to try and establish what actual difference there may be, right? Are we rejecting the null hypothesis that frequently is there's no difference between these groups? Are we retaining the null hypothesis, et cetera? And the estimation is just getting the value of an unknown parameter. So whereas, again, hypothesis testing, we're saying, yes, there's an effect, no, there's no effect. Estimation is how big of an effect is there. So we can have either a point estimate or an interval estimate. A point estimate, like its name suggests, is a single value with which we're trying to be very precise. So for example, if we're trying to estimate what is the average age of students at UAH, we could sample 200 students at random and have a fairly good point estimate of what that average age would be. I'm going to say 21 and a half years old. It's a single datum. Again, datum being the singular of the plural data. The interval estimate, on the other hand, is going to give us that range of values and has the advantage of providing a greater confidence in our answer than a single point. Kate says, so there always is an effect with estimation. So you're typically using estimation once you have an effect. And we'll go over that in just a second, why that would be. People do give estimates when there's no effect, just kind of try to give you a directionality. But it's usually only used once you've got a main effect, right? You've rejected the null hypothesis. So for example, you might want to estimate that the mean age for students at UAH is somewhere between 20 and 23. So while we get a point estimate being very precise, it's likely that we're off to some degree, right? It's an approximation at a single point. But with these interval estimates, there's a very good chance that the actual mean age is between these two values, right? So we're conferring some degree of uncertainty to our estimation. What we typically call these estimate range, these range estimations, confidence intervals, right? So we can say this is the 95% confidence interval. What we're saying there is we have essentially 95% of the time, based off our estimates, the true value is going to fall within this range. You can have a 95% confidence interval. You could have a 99% confidence interval. You could have a 80% confidence interval if you wanted to. All right, so let's just take a really kind of conceptual approach right now. If I wanted to have greater levels of certainty, if I wanted to have greater confidence that I was encapsulating the true value, would those confidence intervals get bigger or smaller?
Bigger.
Bigger, exactly, right? So let's think to the average age estimation of students at UAH. I could have a 95% confidence interval that says it's probably between 20 and 23, right? That's a pretty darn good guess. But let's say I wanted a 99% confidence interval. I said, okay, well, 99% confidence, it's almost certainly between 18 and 25. Let's say I wanted a 99.9% confidence interval. I wanted to be almost certain that I was encapsulating the true value of the age. We could then say it was between 10 and 100, right? So conceptually, again, as we increase our confidence, we have to increase the estimation parameters. And so to get to kind of Kate's point here, let's say we had some spectrum, right? And there's the 0 point. So everything over here is negative, everything over here is positive. One thing we're likely to do with any of these tests is to say, what is the confidence interval for that difference score? So let's say our point estimate is 3, and we've got a confidence interval of plus or minus 2. Right? We can say with 95% confidence that the true difference between those groups is likely between 1 and 5. However, one of the other ways you see this and why this is an inferential statistic is because if I were to say, okay, the true value is -3, or the point estimate, excuse me, is -3, but I've got an error of plus or minus 4, we now say our 95% confidence interval would range from -7, whoa, there we go, to +1, which means we can't say with certainty that there's even an effect, right? Because part of this confidence interval not only includes 0, that there's no effect, but actually includes the opposite direction of the effect. All right, and so it's typically the case that you'll see this confidence interval presented only when there is an effect, and so it's not encompassing 0. However, you'll also sometimes see these confidence intervals presented when they do include 0, just to give you an indication. And you'll see that in the video I'm going to show in just a little bit here. Questions about anything so far?
Is there
So if
an
that
is there an abbreviation for confidence interval?
Yes,
Like everything
I'll go
else
to that in
we've
just a
done?
second. I'm going to answer.
Okay.
Yes, I'm going to answer Sunny's question real quick. So yes, if it includes 0, it has no effect, right? We say that we're not rejecting the null hypothesis if that confidence interval is encompassing or encapsulating 0. So yes, ACE. The equation we'll go over in just a minute, but the actual way you would write it, so if you're doing a 95% confidence interval, it would be 95% CI is how you'd be representing that. Other questions? Awesome. All right, so there's an estimation procedure that accompanies each of those 3 t-tests that we've already covered up to this point. And the estimation process begins with the same t-statistic that's used for the corresponding hypothesis test. All right, so we should all know at this point how to calculate that t-statistic for the independent measures or the repeated measures t-test. But they've all got that same sort of conceptual structure, right? It's a sample statistic minus the unknown parameter divided by essentially how much variance there is. But we're using standard error rather than variance. All right, so that T equation, that top could be mu1 minus mu2. It's supposed to be mu, not a W. It could be D minus that hypothesized population difference. But again, it's all the same conceptual structure. All right, so this shouldn't be anything new. To get your confidence interval, you're taking the statistic, right? So that difference score in some cases, or that mean value, and then you're adding and subtracting your t value, the t-score you got, times the standard error, right? The same standard error that you use to get the t-statistic, you're using here. So again, what you'll get, for example, is 100 plus or minus 15. Right? That's just the easy way to write it. But you could have also written that 85 to 115. Right? Those mean the exact same thing conceptually. Sorry, what's the what? So it depends on what you're trying to estimate, right? And so if you're estimating the mean difference, that statistic is going to be, what is the average difference score between those? That make sense? If you are trying to estimate, what is the mean for a sample, that mean for the sample would be that statistic. So whatever your value of interest is your statistic. So again, just to kind of represent what we've got here, That mean 1 minus mean 2, that mean difference, plus or minus t times that standard error for the repeated measures. It's that mean difference, plus or minus t times the standard error of mean differences, etc. So again, it's the same conceptual structure. Whatever that statistic, whatever that thing is you're interested in, why you even ran the test goes first. Plus or minus t times that standard error. If at any point your confidence interval, at least for the purposes of this class, is asymmetrical, you screwed up, right? You should have a single point, and because you have plus or minus a value, should be equally located on either side of that point for that confidence interval. So this is essentially just echoing what I said before, just putting it all into text. Again, whatever that value is of interest to you, you're putting in as the statistic. For that point estimate, you're just using a 0 for the t, right? That's just essentially a way of saying it's the same equation. You're just, at this point, just taking that point. That first initial thing in that confidence interval equation, that's your point estimate, right? The whole thing together is your confidence interval. When you're doing the interval estimate, you have to find the corresponding t value for whatever that confidence interval is that you want. And so if we've got a 95% confidence interval, we have to find what is the t statistic for 5% and 2 tails for the degrees of freedom that we have, right? We have to look that up in the back of the book and get that value. If you wanted to do a 99% confidence interval, it would be 1% and 2 tails for those degrees of freedom.
Could you please repeat that last part? If it's a 99%.
Yes. Yeah, if it's 99% confidence interval, you're then looking up 1% and 2 tails, and then for your given degrees of freedom for that.
Makes
Right,
sense.
so if you go and look at the back of the book, yep, go look in the back of the book, you'll have 1 tail, 2 tail up top, you'll have your degrees of freedom on the left-hand side, and what you're looking for is that very rigid, that cutoff value, that t critical value that you use to make your decision, you're then using for this confidence interval. So as we already talked about, if other factors are held constant, increasing the level of confidence from, let's say, 80 to 90 will increase the width of that confidence interval. Right? The more certain you want to be, the bigger your net has to be.
I have a quick question before you go on,
Yeah.
which you might have already said, but so if we're looking for, if we were looking for 95%, our T statistic would correspond to the body or the tail?
Neither. You're looking at the unit normal table. And so what you need to look at is the T distribution table. So T distribution table doesn't have body or tail. It just has one tail or two tails. And so that will be what you're using there.
Okay. So then,
Good question.
so then if we're doing, so like if we're doing like, if we're trying to find like 95%, would we use the 0.05?
You would use 0.05 and two tails.
Right. Okay. So we basically, you would subtract the difference from 100%, and then you would use the two tail portion.
Correct. Yep.
Okay. Okay. Thank you.
Of course. What do you say, Sonny? Yeah, if you've got a degree of freedom higher than whatever that T table goes to, just use that infinity number. Good question. Conversely, if you want less certainty, you're going to decrease that width of the confidence interval. The width. Oh, go ahead.
Back to what I was just saying. So we use the two tail because we're looking for, because our interval is looking at plus or minus, right?
Mm-hmm. Yep.
Okay. I was just trying to glue all that together. Okay. Thank you.
Yep. Great. So the confidence interval is also inherently tied to the sample size, right, through that standard error measurement, which means that a larger sample is going to reduce that standard error, which is in turn going to reduce that estimation range. All right, and just think about this intuitively. I'm going to have a lot more certainty in what the average age of UAH students are if I sample 5,000 UAH students than I would if I sampled 5 UAH students, right? So the smaller the sample size, the bigger my estimation range has to be, because it's a lot more likely that I've got some outliers skewing data when I've got a small sample than when I've got a big sample. So again, this just serves to highlight, once you've got a confidence interval, it's going to range between two values. And so if this is our 95% confidence interval, we can say with 95% confidence, the true value for the difference between mu1 and mu2 falls between 4.76 and 11.24. Questions about any of that? Awesome.
Wait, I'm sorry. Okay, so
Yeah, go
on
ahead.
that graph that you just pulled up, it said 95%. So that line in between 4.76 and 11.24 is 95. Is that what it's saying, or is that just up there talking about the confidence? I don't really understand.
Yeah, so it's just signifying the range between these, right? So it's saying that with 95% confidence, we feel like we can say that the difference between mu1 and mu2 falls anywhere on this line.
And
it could be 4.76, it could be 82. What's that?
Like, I'm asking, is that given to us, or are we supposed to know that? Like, are we supposed to say that when we see a graph like that?
So you are supposed to know, if a confidence interval is given to you, what that conceptually means, right?
Okay.
If I give you a confidence interval, if I say the 95% confidence interval is between 4.76 and 11.24, you have to know that with 95% probability that the actual mean difference between mu1 and mu2 is going to fall between those two numbers.
Okay.
Does that make sense?
It kind of does.
Okay. Do you know what doesn't make sense? I know that's always a tough question.
Is the 95 already given to us, or are we supposed to know that? Is that that's what I'm kind of confused about.
Okay. So where does the 95 come from?
Yeah, where does that come from?
So that's a determination you make. The standard is usually 95% in the same way that we're using a 0.05 for p value, but you could make a 99% confidence interval, right? If you really wanted to be certain, you could make a 99% confidence interval, but it's typically 95%.
Okay, I understand.
Cool.
Okay.
Awesome. All right. So typically, when undergraduate statistics classes are taught, we teach you about the p-value, and we hold that up as the holy grail, right? Less than 0.05, you reject the null hypothesis, life's good, right? Above 0.05, you retain the null hypothesis, and that's harder to publish. But I had a really jarring experience when I went to grad school because I was taught it that way. And then I got to grad school and they said, everything you had been taught was wrong, right? That the p-values are actually stupid and don't tell you what you think they're telling you. Right, so if I told you that we're using a p, again, p stands for probability of 0.05, and I asked you, how many times should an effect with a p of 0.05 fail to replicate itself? What would be your default answer?
How many times does it fail to
some people will,
replicate?
Yeah, so Sunny said 0. A lot of people's intuition is it should either never fail to replicate because it's an effect, or 0.05% of the time, right? Because remember when we talk about our type 1 and type 2 errors. But in reality, as I will show you in just a second with this video, an effect of 0.05 fails to replicate about a third of the time, right? And so we have this intuition that says an effect is always an effect, but that's not actually true, right? And so one of the things y'all may have come to hear about over the last, I don't know when this first came up, probably when I started grad school, so probably about 8 years ago, there was this quote unquote replication crisis, wherein some researchers at my alma mater, UVA, went out and got people from different subdisciplines within psychology and said, we want you to pick the most important finding in your field and just do a direct replication. Do everything they did the exact same way. And they got 100 of those, right? And these are all effects, right? These are all things that have been found before and have become foundational. And one of the things they found in doing this direct replication is this massive amount of failures to replicate, right? This is a big issue, right? Because we're now basing entire lines of research on this idea. But if it's failing to replicate, it may not even be a real idea. It may not even be a real effect. And so a whole bunch of criticism came out about psychology, and there was a lot of soft science bashing, right? Oh, okay, well, psychology is not a real science, so this is exclusive to psychology. And then other fields said, well, why don't we try to do the same thing? And the exact same failure to replicate rate came out in things like cancer studies. Right, think about how important that issue is. If you have 1/3 of studies that are saying, yes, this is an effective cancer treatment, which aren't an effective cancer treatment, right? After the fact, it says, whoops, actually turns out not to be. You devoted a ton of resources, potentially people's lives, in the attempt of understanding what's going on, right? And so this is why this presents an issue, because this is not necessarily a methodological thing. It's a statistical thing. And so there's this whole movement. It's kind of, if you could have a hipster underground movement in academia, it would be this. But to try to get people to kind of abandon the p-values, or at least use the p-values in tandem with things like estimation. Right? I'm going to show you a video now which shows you why that's so important. Now, after today, we're going to just kind of ignore everything I said today about p-values, and we're going to continue on because that's part of the foundational understanding. And when y'all go to grad school eventually, or go into any sort of data analytic positions after graduation, you'll kind of learn some of these adaptations, right? And there are a lot of more advanced statistics, so things like Bayesian probabilities, named after Thomas Bayes, to get around this. But I want to at least raise this concern with y'all so you're at least familiar with it when it comes time to having these conversations. Plus, if any of y'all go to grad school and can address before you're even in grad school the fact that p-values should not be the holy grail, you're going to earn a lot of brownie points. So give me 1 second here. I'm going to transition back to my normal computer. So hold on, Zoomies. You're not going to be able to hear me for just a second. All right, Zoomies, can you hear me? Cool.
Yes.
Cool, cool, cool. All right. And yes, Ace, you're very right. It is worrying.
The p-value. Many researchers make it central in the way they think about their data and make their research decisions. But should we trust it? One interesting thing is that the p-value has hardly been studied. We know very little about how researchers actually think about and feel about p-values. Great topic for research. So let me speculate. I think that usually people think about p in terms of intervals like this. So p less than 0.001, 3 stars, all the way through to p greater than 0.10. And think of p as a measure of strength of evidence. And this elicits significance language from very highly significant down through here, and values between 0.05 and 10 approaching significance. How do you know it's not running away from it as hard as it can go? And we want this language to indicate truth. We desperately want to know about the world and know about truth. There is an effect, or there is no effect, or perhaps even a zero effect. And this evokes emotion. P has affect attached. And it really matters. People make decisions in the world based on values of P, whether you get tenure or not. And so it's central in everyone's thinking about research. But should we trust P? Let's think about P and replication. If P reveals truth, surely if we did the experiment again, it should reveal the same truth. If we get P 0.05 and repeat, Of course, we wouldn't get exactly 05, but what would we get? Something in 04, 06 or 03, 07? Or should we think about an even wider interval? Well, let's do some simulation and investigate. I'm going to take a very standard sort of experiment, 2 independent groups, each of size 32, so a control group and an experimental group. And here I'm assuming there's a control population normally distributed of, say, well-being scores, which has a mean of 50. And the experimental group, let's suppose they've had your skillful massage for an hour, and on average this has increased their well-being score by 10 points. These normal distributions we're assuming have standard deviations of 20, so that's an effect size in the population of 10 points or 10.
So really quick before he continues, what he's talking about here is setting up the ground truth, right? So he's going to be sampling from each one of these distributions, but he's saying this is what the ground truth is that we're going to be running the simulation off of.
Over 20, that's 0.5 of a standard deviation. Cohen's delta of 0.5, or standardized mean difference of half a standard deviation. So let's run an experiment, and the 32 blue dots are our 32 people who read the magazine instead of having the massage, and there's their mean and 95% confidence interval. The 32 red experimental scores and their mean and confidence interval. Let's turn on a difference axis there with a 0 lined up with a control mean, and this experiment estimated the difference, the advantage of the massage, at about 3 points. And there's the difference on this differences axis there, and here's the confidence interval on that difference. Let's do the experiment again, and that first result drops down, and this next experiment estimated a difference of about 5 points. And this next one about 11 points. And if we run this experiment a number of times, exactly what we expect happens, and these means and confidence intervals bounce around, the dance of the confidence intervals. Now remember, of course, in real life, we don't know the populations, and we know only a single one of the experimental results. And so we have to imagine in our mind's eye some populations and imagine these confidence intervals bouncing around. But does this single confidence interval tell you something about what's likely to happen on replication? What the whole infinite sequence of confidence intervals around? So a confidence to represent joy. 2 stars, still very happy. 1 star, okay. That's the questionable one, and you don't want to hear this, do you? There it is. Oh, deep depression of p greater than 10. Okay, our first experiment, our confidence interval just included the null hypothesis of 0, and so that means not significant. We'll get a p-value a bit greater than 0.05, and indeed we do, 0.095 question mark. Let's do another experiment, and this time the confidence interval overlaps 0 a bit more, so we get a p-value greater than 10, dark blue. Let's do another one, another one, another one, and now I'm going to run a whole lot. And let me stop it at some random point.
So again, what you see here is that pulled from the exact same distributions, but the ground truth of an effect size of 0.5, which is a medium effect size, it's a pretty good effect size, you can see how much variability there is in these p-values, right? From 0.02, 0.01, all the way up to, let's see, where there's 0.35, 0.5, 0.329, 0.000, right? And so you can see why this starts to present an issue. And so
now, just to recap, here we have the dance of the experiment, which amounts to of the different p-values we get.
You can see how these different p-values stack up, right? You can see the range from, again, these same distributions that is being pulled from. You can see how much it jumps around, but one of the things you'll notice is that these confidence intervals, all, not all, but most of which seem to encapsulate that 10-point where'd we go? Back here. That 10-point effect, right? So we've now got a fairly good understanding based off of these confidence intervals, what probably the true effect is based off of the summation of all of these, right? And so if we're relying only on our p-values, you can see we're going to have very different interpretations based off of our sample. And so this serves to highlight the consequences of relying on those p-values rather than something like the estimation. Questions about that? Cool.
Will we be tested on that?
On this itself?
Yeah.
No, but it does. So you may be asked, what are some of the issues with p-values, or why might you want to use a confidence interval? But I'm not going to ask you to kind of create this entire replication.
Okay, thank you.
Mm-hmm. Somebody else was asking a question. Yeah. Well, so not the same sample, but the same population he pulled from, right? And so the population had that normal distribution, and he pulled samples from that, right? And so as we've talked about all semester, pulling from those populations, you're going to get varying kind of sampling errors. And those slight sampling errors are what were causing that p-value to jump all over the place for that. But yeah, he was pulling from the same. So again, what he was modeling was a ground truth of there actually being an effect, right? But that p-value was jumping all over the place because of just kind of the nature of using those p-values.
Did you say there was like a 3% chance that there was like a difference, or did you say there was 30%?
So it's about a 1 in 3 chance if you have a p of 0.05 that it won't replicate again.
Okay.
And that's inherent to statistics, right? I mean, so that's not a psychology thing. It's not a cancer thing. It's just using that kind of flawed statistical approach for that. All right, so we have about 20 minutes left. If you want to go ahead and sign off, you're more than welcome to. I'll stick around for the extra 20 minutes here and answer any questions y'all have about the exam or anything else. Yeah. So.
I have a question, even though I just...
Sunny's got a question.
Okay.
How would the estimation question be framed? I would say, given this certain mean difference and a sample of this size, what would be the confidence, the 95% confidence interval for that range? Mm-hmm. Yep, you would use that formula, right? And so you have the standard error you would have calculated, you would have that mean difference, and then you would find that T critical value that you're using and plug that in for that confidence interval. Yeah, Dallas, what was your question?
Well, I have two now. Well, the first one was, could you just give us an example on the estimation problem, like for tonight, like you usually do, so we could just see what it looks like?
Yes, yeah, you'll still get a practice.
Okay. And for another one, for the test, I was struggling on independent measures, like the last part, and I just wanted you to just kind of go over it just a little bit more.
When you say the last part, what do you mean the last part?
When we started going over like the pooled variance, that's like the whole thing, right? Or
yeah, so
really, yeah.
Yeah, so the pooled variance is going to be, 1 second here. The pooled variance you're using is just the average variance for those two different groups, right? So you have the variance for group 1, you have the variance for group 2 over degrees of freedom for group 1 plus the degrees of freedom for group 2. Or excuse me, nope, ignore what I just said. Sum of squares. All right, so using that pooled variance, rather than getting the individual variance for each group, you're putting the two variances together and trying to estimate what is the variance for the population based off of that extra information that you have. Does that make sense, Dallas?
Yes, it does.
Okay.
Thank you.
Cool. A said, last test you gave us which formulas we need. Could you do that again? Yes. So, I mean, all the variants, or excuse me, all of the same equations you needed for the first exam, plus you're going to need the T for independent measures, the T for dependent measures. You're going to need the confidence interval that we went over today. You're going to need the one sample t-test. You're going to need, again, all the same ones from before. You're going to need the sum of squares, you're going to need the variance, you're going to need the standard deviation. You're going to need the standard error, the standard, so the standard error is going to be different depending on which test you are running, right? And so it's going to be the same conceptual idea, but how it's represented is going to be slightly different in there. So you're going to need to know the equation for R squared, for Cohen's D. What are the ones am I missing?
We talk about like
Fine,
pool variance and stuff.
T-value.
Yeah, so the T, yes, so the T is before. So yeah, how
Pool
to find
variance,
pool
right?
variance, yes.
and then the sample standard error equation. Oh yeah, I think you wrote that already.
And then I'm sorry, you said the what?
I said estimated standard error, but I think you wrote that. Yeah.
Yeah, so what that standard error looks like. I think that's it. Essentially, any equation I've written on the PowerPoints, you should have on your sheet. Yep. What are the questions?
I don't know. Is there a way we can work out a confidence interval problem?
Yeah, give me one second. What did you say, Sonny? I got to speak up. I'm an old man. Because we were doing something different, right? So we're using that when we have a known value, right? Those are very different types of questions in there. So the t-test we have is when we're trying to make estimations about the population, right? And so if you go back and look at the types of questions we're asking when we're using the Z table versus the T distribution table, they're fundamentally different in kind of the structure of what type of question they're asking there. And so you're using the t-distribution table. Again, if you have two samples, you're using the t-distribution table. If you have one sample but an unknown population mean, right? And so you're using the z if you've got a known population mean and standard deviation and things like that. That make sense? So Caleb, you said you wanted to work out a confidence interval problem here?
Yeah, if you don't mind.
Yeah. So again, for the confidence interval, what we're going to need is we're going to need the the value, right? The statistic that we're interested in, plus or minus the t critical times that standard error, right? And so standard error depends on what you're doing. So let's just do for a mean difference, right? And so let's say that we have a group of 5 people, right? So our n equals 5, and we've calculated that that mean difference is going to be 3. I don't know, let me look this up real quick. T-distribution table. All right, so if we have 4, it's going to be 2.77. So where did that go? So our T critical equals 2.77. And then we will have had to have calculated our standard error. But let's just say we've got a standard error that we've calculated off of the test. And so we've got a standard error of 1.2.
We would just assume that we're doing a 95% test or 95%.
Yeah, I think
95%.
unless otherwise specified, just assume 95%.
Okay.
And so we would then say our confidence interval is equal to 3 plus or minus, let's go back here, the T critical, so 2.77 times that 1.2. And if I do that, 2.77 times 1.2, 3.32. So our confidence interval would be 3 plus or minus 3.32. So would we reject the null or retain the null test for this? Or hypothesis, excuse me.
We would hold on. Yeah, we would reject it. Right?
It does have 0, yes. So we would fail to reject, right? Because this is saying that, say, here is 0, saying our point estimate is 3, so it'd be 3 here. And we're adding and subtracting 3.32, right? So if we subtract 3.32 from 3, we get negative 0.32, and we get positive 6.32, right? And so this confidence interval, we would say we fail to reject the null hypothesis because it includes that 0 point in there. Ace says, will the t-distribution table be given to us on the test? It will for everybody else, but you're going to have to memorize it. Yes, I found the t-critical through the degrees of freedom. And just kidding, Ace. Yes, you'll get it as well. Yeah, so the t-critical is through the degrees of freedom. Knowing those degrees of freedom, what proportion you want into tails, etc.
So whether or not we accept or reject the null hypothesis is based off of our final interval, right?
What do you mean by final interval?
Like our the negative 0.32 all the way to 6.32. If one of those is outside of the null hypothesis, then we can reject it.
Yes. Yeah,
Okay.
so if, let's say instead of plus or minus 3.32, it was plus or minus 2, then you have your confidence interval going from 1 to 5, and it's not including 0, and so you would reject the null hypothesis.
How do you put that in your calculator? I'm kind of, you lost me with I understand what you're doing, but I don't know how to put it in my calculator, the 3 and the plus or minus 2.77.
You'd have to like
And,
do them as like two different like
oh,
equations. Like you do 3 plus the 3.2 equals that answer, then 3 minus 3.2.
Yeah, this is just a shorthand for saying one bound would be 3 plus 2.77 times 1.2, and the other would be 3 minus 2.77 times 1.2. Having this plus
so
or
you're
minus.
gonna have two answers. You're always gonna have two answers, right?
Yes, exactly. Because it's an interval, you have to have two bounds, a lower bound and an upper bound.
Could it ever be plus 0 or plus or minus 0?
So you would have to round down to 0 because the confidence interval itself is taking probability, and you'll never have a 0 probability. I mean, you could have a functionally 0 probability, but you'll never have plus or minus 0 if you're trying to get the actual interval, right? So for the point estimate, you're essentially doing plus or minus 0 because you're just trying to get that single point. But when you've got an interval, you won't ever have plus or minus 0.
That makes a lot of sense.
Good. Andrew says, is this exam going to be formatted similar to the first exam? This one is going to be almost exclusively just calculation based, right? And so if I were y'all, I think it would be a very smart study strategy to go on and look at the practice problems I put onto Canvas and create your own practice problems and just make sure you could do those all the way through. Dope indeed, Amber. Okay, Moss, what else?
Can you reiterate what you were saying about on the same page? You were saying something about we would fail to reject it if it was 0. With this example on the page, you were saying.
So we would fail to reject it if the confidence interval included 0, right? And so if our confidence interval is 4 plus or minus 5, right? That means that our confidence interval is from -1 to 9, right? Because 0 falls on this, we would say, well, our 95% confidence interval is saying that there is a chance that there's no effect, right? And because there's a chance there's no effect, we're going to, out of an abundance of caution, say that we're retaining the null. We're failing to reject the null. Does that make sense?
Can you please do another example on that? I don't understand that.
Okay.
And your thing is flipped, so I don't know if it's that, but I can't really see the answers that you have on the board. Like, it's not, you know how you can like transport your iPad and we can see like the white paper? Well, we see it on your board and it's like flipped, so I can't really see it because your head's like right there, so I can't see all the numbers you put. So
There's another window that has just what he's seeing.
Oh.
Yeah, it should be sharing that.
I'm sorry, it's not on mine. I'm sorry.
No, that's fine.
Okay.
Yeah, I will do another example in just a second. Evan, there will be essentially just 4 big questions, right? They're going to be sub-questions within that. Like, I want you to give me values along the way. But essentially just 4 big questions to work out. And for this one, I'm doing it a little bit different. I want y'all to show me your work along the process. You're gonna have to type it into just an essay box. because that way it's going to allow me to see where y'all went wrong if you did go wrong, and at least give y'all partial credit. If you get the right answer and don't show me any work, I'm not going to give you any credit for that problem. It's also kind of just a cheating fail-safe, but it will allow me to see kind of when you went wrong, where did you go wrong? So give me the values along that way.
How do we show our work if it's going to be online?
So you're just going
Like
to
our
type in.
work is on paper.
Yeah, so it doesn't have to be, I mean, it doesn't have to be exactly perfect, but just show me like the type of calculations you're doing, right? And so, you know, the standard deviation divided by the square root of n, right? And so I'm seeing at least along the process, because that way, if you accidentally typed in a number wrong on step 1, I'm not taking off all the points for later on. I can see where you got a wrong value and you had the steps right. I just wasn't able to give you the full credit because you got the wrong answer, but you got the steps and process right.
So we're going to be typing our work in on the program?
Yes.
Okay.
Yeah. So, I mean, it doesn't need to be anything.
That's a little bit different because before we put all our work on paper. That's why I'm confirming.
Yeah, you can still do it on paper, but just type in things, right? So if I've already calculated, you know, I'll just type in, you know, my mean equals 4.5. So the standard error is going to be equal to the standard deviation divided by square root of n. And so, you know, for that, I know I've got 2.3 divided by square root of 9. So 2.3 divided by 3. And so that way, you know, if you accidentally had 4 up there, I know where you went wrong.
That's something you can follow.
Yes, exactly.
Okay, good. Thank you.
Amber says, when you do the problem after class for this confidence interval, think we can get the entire problem where we have to find the t-score and everything? Sure. Yes. We'll do soup to nuts on that one. All right. We are out of time here. I will stick around for a couple of extra minutes if you have any other questions. Otherwise, good luck studying for the exam. Practice, 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 practice. Do the problems as you see them on the Canvas page. If y'all have questions, let me know.
Bye.
Bye. Thanks, Evan. You too. Thanks, Nancy.
Dr. Tenhunfeld.
Yes.
Okay, so I'm still, I still don't know what's going on with that, the confidence interval. So with the example that you had, and you were doing the 4 plus or minus 5, and then that gives us a confidence interval, -1 all the way to +9.
Correct.
So that, so is it like, does that mean that anything that falls within this interval, we fail to reject the null hypothesis?
So what we're seeing in that range from -1 to +9 is that we can be 95% certain that the true difference between those groups falls somewhere in between these two. If they all fell in the positive direction, so let's say instead of -1 to 9, it was 1 to 11, we would say there's an effect, right? We don't know the size of the effect, but because every possible answer is in the positive direction on here, we would say there's an effect. Similarly, if it was all negative, we would say because it's all in the negative direction, there's likely an effect. But because what we have here on the -1 to +9, we're saying that a majority of what we see here is in the positive direction, but
because of where it, where the interval's set in terms of 0?
Yeah, so we can't rule out here that the true effect is 0 or even potentially in the opposite direction. And because we can't rule that out, we're saying, well, we can't define that there's an effect because in reality, it could be positive, it could be negative, it could be nothing. We don't know. Does that make sense?
Yeah.
Cool.
Is that related to variance as well, saying that if it crosses over, so if it's supposed to be in the positive and it kind of crosses over into the negative as well, there's probably a larger variance, which would...
Yeah, I mean, because because one of the parameters you're using to make this estimation.
I meant variability, sorry.
Yeah, no, that's good. Because one of the parameters you're using for this estimation is the standard error, which is a function of the standard deviation, is a function of the variance. The bigger the variance, the bigger that estimation window is going to be, right?
Right.
Yeah, it's all related.
Cool.
So like when you ask on the exam for an estimation related question, are you just going to be looking like, are you going to be asking for like the actual interval itself, or are we just, is it more like interpret the interval? And then our interpretation of the interval would be that most of the scores are going to be positive. Like, is that?
It would be like, I would give you, let's say, a repeated measures test, and I would say, what is, do you reject the null? Do you fail to reject the null? And what is your parameter estimate for the mean difference between those two, right? And so you would go through the t-test, you would reject the null or fail to reject the null, and then you would take what you found for your mean difference. You would find that t critical, you're multiplying that t critical by the standard error that you already established to get that range, right? And so we would say, that.
So we would find the t statistic as normal first.
Yes, yeah, this is an addition.
Okay. Sorry, I guess I didn't get that part. I thought we were supposed to use the interval and somehow figure out a t statistic. So I was a little concerned. Okay, so we would find the t statistic like as normal, and it's kind of like Cohen's d and r squared. Like you're just like,
it's an after the fact kind of addition.
Okay.
Right? I mean, you can do this in isolation if you wanted to, because it's technically an inferential statistic, but for purposes of this class, it's almost always going to be just an add-on.
Oh, okay. And then so how we find the, well, I guess how we find the t statistic always is the same, but I guess how we find the confidence interval differs depending on if we're doing independent samples or if we're doing repeated measures. We would just use those different equations to figure it out, right?
Yeah, so I mean, it's the same conceptual body.
Okay.
In that you're always, it's the stat plus or minus the t crit times standard error. It's just, what does that standard error look like? And what does that statistic look like? Going to be a little different depending on if you're doing repeated measures or independent measures.
Wait, so that t in the, okay. Sorry, I didn't realize that it was the t crit.
Yes, yeah, so it's for how many degrees of freedom, what is that cutoff for, 0.05 in two tails for a given degrees of freedom.
Okay.
Is it possible to do this as well with the z crit and the z scores? To do the confidence interval or no?
Yes, yeah.
Okay. But will we be doing that with just the t's or both?
For this exam, you won't have to do it for the z.
Okay.
Okay. Also, something we were kind of trying to figure out in past, are you going to be pretty explicit about whether you're looking for a z-score or a t-statistic, or is that something we're going to have to really make sure we understand in the wording? Because when we were doing hypothesis testing, some of the questions between the t-test and just a regular hypothesis test using the z-scores kind of look a little similar. So we were kind of trying to figure out how we're going to know to use the unit normal table, or if we're going to use the t distribution.
Yeah, so y'all kind of lucked out this semester with everything being online because I can't give all that much. Normally I would staple to the back of y'all's exams the unit normal table and the t distribution table. But for this one, I'm only giving you one. And so I'm not explicitly stating it, but you can't get the wrong value by going to the wrong table, at least in this case.
Okay. So it's an exam focused on the t-distribution. Okay.
I have a question. Like when you do your examples, can you just post another example on the independent measures? That's the most unit that I'm confused on because it's just so much at the end with square rooting them and stuff. I'm struggling on that, and I just want you to do it again.
I will try to get around to that. My suggestion would be, based off of what we talked about so far this semester, being able to create your own practice problem or do practice problems in the back of the book for that. I will try to get around to working out another one of those problems, but with y'all doing the lab and having access to SPSS, you can kind of create your own problem and see if you got that right answer using that video template as kind of the how to walk through each of those steps.
Okay, thank you.
Mm-hmm. I don't know, Amber. Yeah, that would be something Luke would have to answer. Oh, Caleb, and can you say yes? Awesome. All right, my computer's about to die, so I'm going to go ahead and end things here. If you have other questions, send me an email, and I'm happy to set up a meeting. Of course, thank you, Kenya. And we will get rocking and rolling on the exam. Good luck.